Good morning, guys, of grade 11. Today, inshallah, we're going to start in section 2 of chapter 18. We're still talking about the chemical equilibrium. In that lesson, we're going to talk about shifting equilibrium, how we could disturb or how we could make the equilibrium somehow drifted into one of the two directions, okay, the forward direction or the reverse direction. So, just to remember what we said last time, we said that in equilibrium, reaction, that means there are two reactions that are working in two different or in opposite directions. Okay, one in the forward reaction, that means from the reactants leads to the product, while reverse reaction, that the product is gonna react to form the reactants one more time. And we said once the equilibrium is established, actually the concentration or the ratio between the reactants and products will be somehow constant or fixed, because already we are in equilibrium. That means at the moment that the reactants are combined to form the products will decompose to form the reactant and so on. And we said this equilibrium will be established and like this will be constant as certain temperature and certain conditions. But what would happen if these conditions changed? Actually, if this condition changed, that will alternate or that will shift the equilibrium. So the equilibrium will not be, or the two reactions will not happen in the same rate as usual. In that case, there is a kind of shifting happen. One of these two reactions will happen in a higher rate than the other. So which one will be in higher rate? That's the question. So that leads us to predicting the direction of the shift. Which direction, the forward direction or the reverse direction, will be or will happen in higher rate? Actually, there is a scientist, his name is Louis Chatelier. So Chatelier actually put a principle, or who just said a principle that helped us to predict once the conditions of a chemical reaction changing, how the equilibrium will be alternated or how it will be shifted. So what he said that in a system at equilibrium, okay, is subjected to a stress. A stress means change in the conditions of the equilibrium, like changing in temperature, concentration, pressure, okay, and so on. So that's considered as stress. So the equilibrium reaction or the reaction will, okay, move faster in the direction which relieve this stress. That mean, okay, that if the forward reaction will relieve this stress or cancel this stress, okay, so the forward reaction will be faster than the reverse. If the reverse reaction is the reaction that's gonna relieve this stress, so it will be having faster. So let's get an example to understand how this works. So let's start by pressure. And once we say change in pressure, of course, we talk about gases, because gases is the only state of matter that could be compressed, or during a chemical reaction, gases, the effect of pressure on gases could be observed, of course, but in solids or liquids, that's hardly to be observed, or there is no effect. So does pressure or changing pressure affect the different, okay, gaseous reaction? Actually not. To ensure that a reaction is could be affected by change in pressure, we must be sure that the number or the total number of moles of reactants is different than the total number of moles of the products, which means here, okay, as you can see, in this reaction, nitrogen reacts with hydrogen to produce ammonia. So in this reaction, we could find that the total amount of moles in the reactants are 4 moles, 1 mole of nitrogen plus 3 moles of hydrogen. They gonna produce, okay, 2 moles of ammonia. So here, that could show to us that the pressure could have effect. Why? Because pressure, simply, what is pressure? Pressure means the force that applied over area. And once you apply force over area, that means somehow you are gonna decrease the area. So the particles, the more particles found in a smaller area, okay, that's mean they have higher pressure, okay. So once the particle numbers decreases, it means here, okay, the pressure decreases, or that means that's gonna be there is effect for the pressure. But if the number of moles in the two sides are equal, so that means there is no effect of the pressure, because the number of moles before the reaction equal the number of moles after the reaction. So in that case, the pressure will not have any effect. So in this equation, pressure could affect because we have different number of moles of reactants than the number of moles of the products. So what happened here? Okay, so first of all, once we start to increase the pressure, increasing the pressure means, okay, that the nitrogen and the hydrogen is gonna be under pressure, which means they are too closer to each other. That will lead them to try to release or try to cancel this pressure. How they can do this? They are gonna try to react more to produce ammonia. Why? Because each 4 moles of nitrogen and hydrogen, they're just gonna produce 2 moles of ammonia, which means they are gonna reduce the number of particles. So like this, the pressure will be less because 2 particles will be in the same area, so that will be less pressure. So here like this, by increasing pressure, we're gonna find that nitrogen and the hydrogen, they are gonna collide more often, okay, rather than the collision between the ammonia particles. So in that case, the forward reaction will happen in a higher rate than the reverse reaction. And in that case, the equilibrium is alternated, or the equilibrium is shifted toward the forward reaction. That means it will be shifted toward the right. That means the reactants will have a higher rate of reaction to produce products rather than the decomposition of products to the reactant. Okay, so that's here the idea of increasing the pressure, or how what's happened in the pressure. In case of gases, okay, increasing pressure, it simply affect the concentration. That means an increasing pressure in condition of gases, okay, cause increase in the concentration, because we see the pressure, that means particles will be in a smaller area, so the volume, or the amount of particles in a certain area, that is a concentration. So increasing pressure, that means increasing in concentration. So even here the pressure and increasing the concentration, that will not affect the equilibrium constant, because as the concentration increases, it will be increasing in the 2 sides, okay, that means it will be increasing in the reactant and the product, or the two, okay, sides of the reaction. So the K will be constant and it will never change, okay. So like this here, we could find how the effect, or how that could happen, or how pressure could alternate the gaseous reaction, or how it could shift a gaseous reaction, okay. So as you can see in this analogy here, that's nitrogen and that's hydrogen in normal situation, okay, or at equilibrium. So as you could observe here, for each 3, okay, particles, we have one of the ammonia or one of the nitrogen, and that will lead to the production of one ammonium molecule, okay. So once we are gonna stress, that means we increase the pressure, we added more nitrogen, okay. So like this, we apply more pressure. As you can see, the particles become more in that container, so that means they are under pressure, which makes the collision between hydrogen and nitrogen happen faster and leading for formation of more of ammonia. And like this, that's how it's shifted, okay. So like this, we know the effect of pressure on the gas reaction, or how pressure could alternate an equilibrium gaseous reaction. So then the second factor, which is changing the concentration. Changing concentration actually have the same idea like what we explained here. So for example, if we just get this reaction, okay, A plus B is going to yield A, C, and D. C and D, they yield like A and P. So that equilibrium, that means at certain condition, the concentration of A and P somehow is equal to the concentration of C and D. But what would happen if we just increase the concentration of one of these substances? That, for example, we start to increase the concentration of A, or concentration of B. Okay, so increasing A and P, okay, that's considered as a stress, because now in the container we have more particles of A and P. So as we have more particles of A and B, that means they are become more crowded, which allow them to collide more often. That allow A and P to produce, okay, more C and D. So in that case, the reaction will be, okay, drifted to that side, okay, or to the right side, to formation of more C and D. And this that means the rate of the forward reaction will be somehow faster than the rate of reverse reaction, until a new equilibrium happens or established. So back again to the equilibrium at the new condition. The same happen if we increase the concentration of C and D. Once there are more C and D available in the container, that means they are in a smaller area together, so they collide more often, and that will cause them to react faster than A react with B. That mean here in that case, the equilibrium is shifted to the left side toward formation of more A and B. And that means the rate of the reverse reaction will be more than the rate of the forward reaction until new equilibrium is established. So here, like the idea, okay, whatever the change you do, the reaction will try to move in the direction that cancel this change, okay? So like this here, also the changes in the concentration has no effect in the value of the equilibrium constant. That means the K still as it is, no change here, okay? Because as you change the concentration of one side, the reaction will work to increase the concentration of the other side. So finally, the K will be the same, no difference in that case, okay? So like this, we could find that in different reactions, okay, not all substance will that mean the reactions may produce liquid, solid, gases, and so on. So like this, many chemical reactions involve heterogeneous reactions, and they are gonna have products and reactants in different phases. So we find that pure solids and pure liquids, of course, their concentration never change. So as the concentration of pure solids and pure liquids never change, so we don't use them in the mathematical equation of equilibrium constant. That means once we try to calculate the K, okay, we don't use the pure solids or pure liquid concentration. For example, here, the decomposition of water, okay, or that once water dissociate, okay, to hydronium ion and hydroxide ion. Water is a pure substance, okay, so that's pure liquid, okay, it's not a charged or not ions, so it's pure compound liquid, okay. So that means the concentration of water never changed. So that's once we try to find the K of W, suppose as we know, once we calculate the constant of equilibrium, we see the concentration of the products, okay, yeah, that means concentration of hydrogen multiply the concentration of hydroxide divided by the concentration of the reactants, okay, but in that case, as water is a pure substance, its concentration never changes, so we cannot put it in this equation, or we will not use it, and in that case the K of 4 will equal the multiply of the concentration of hydronium ion multiply the concentration of hydroxide ion. The same here as we can find here carbon calcium carbonate, okay, calcium carbonate leads to calcium oxide and carbon dioxide. So in that case, okay, you could find in that case that the reactant is a pure solid, okay, like calcium carbonate, and the product one pure solid, which is calcium oxide, and the other one is carbon dioxide. So like this, because calcium carbonate and calcium oxide are both are solids, and so their concentration will never change. They are just gonna settle down at the bottom of the tube, and their concentration will not change. So we cannot use them in the mathematical equation of concentration of K. So we can say in that case, the equilibrium of this reaction just will depend on the concentration of carbon dioxide, how much carbon dioxide is going to be produced from this reaction. So like there here, guys, we understand how the effect of how the effect of pressure or concentration could alternate or could shift the rate of the reverse and the forward reaction in case of equilibrium reaction. Then we pass to the third factor, which is change in temperature. So changing in temperature could affect the equilibrium reaction, of course, because actually change of temperature that happen in the reactions or usually in the reverse reaction, we're going to find that there is one reaction is exothermic, that means it emits heat or releases heat. That means the enthalpy of this reaction is going to have a negative sign. Delta H have a negative sign. That means it's a reaction that releases heat. While the other reaction, the reverse one, okay, they could be an endothermic reaction. That means a reaction that absorbs heat or needs heat. And as we know, once equilibrium established, it will be constant as a condition still the same. So one of these conditions is the temperature. That means the equilibrium just happened at a certain temperature. So changing temperature, of course, will affect the rate of the reaction or will make the equilibrium shifted toward one of the two reactions. So increasing temperature, okay, that was meaning adding more heat or adding more energy, so that's considered as a stress, and according to this reaction, okay, or according to the Chatler principle, okay, the reaction will start to move in the direction which start to lower the temperature or start to consume this extra temperature, okay. So let's get an example here, okay. For example, the nitrogen wants to react with hydrogen, okay, to produce ammonia. So you could find that the enthalpy of this reaction equal 92 kilojoule. Okay, so here it's in that case, that means this reaction somehow it got produces here. Okay, or this reaction. Once we change the temperature, high temperature, what would happen? Okay, once we add temperature, okay, we're gonna find adding temperature, that means more heat, that will make the ammonia try to break down. Okay, why here? Because as you add temperature, that means you increase the stress in that side, because here that is the energy in that side. So increasing temperature, okay, that means you increase that side. So that means the ammonia is gonna try to break down to cancel this increase in temperature, and that will shift the reaction toward the opposite direction, or toward the reverse direction, in which more nitrogen and hydrogen formed. Okay, and of course the opposite will happen by cooling down or by decreasing the temperature. Okay, if we decrease the temperature, okay, so by decreasing temperature, that means you cool it down, you cancel this part, so the reaction will try to re-establish that equilibrium, so it will be activated in that direction, or it will work in that direction just to produce, okay, heat, or to compensate the heat which is already absorbed. Okay, so in that case the nitrogen will react more with hydrogen to produce more ammonia. So here that the idea also of that part. So you could find also here, okay, in that way, that this reaction, okay, that once the nitrogen dioxide is going to decompose into dinitrogen tetraoxide, so as energy is released as heat here. So you could expect here, as you can see, this one, its color is brown, while this one, its color is colorless. Okay, so what happens in that case? You could simply find once at 0 degrees Celsius, okay, that means when we decrease the temperature, that means we lose this energy. So that means there is a kind of stress, that means that equilibrium is not established anymore, or is not constant anymore, because we just remove the energy, because cooling down means absorb energy. So that will shift the reaction to make the nitrogen dioxide break more or change more into dinitrogen tetroxide. So they turn to the colorless color. That's why we could find that the color change, okay, into, okay, the bright one. And if we keep cooling, we may reach, okay, more bright color. Okay, so here we find if we increase the temperature, for example, at 100 degrees Celsius, in that case, you add more energy. That means you increase that side. So as this side become more than the equilibrium state, that will make the reaction move in that direction. So that means the dinitrogen tetroxide will work, okay, in the, or the reverse reaction will have higher rate to produce more nitrogen dioxide. Okay, so that means the color will turn to be darker, because in that container we have more nitrogen dioxide than the dinitrogen tetroxide. So while in that's here in the medium, this medium around 25 degrees, that the normal situation, or that the normal equilibrium happened. In that case, we could find that the concentration of nitrogen dioxide somehow equal to the concentration of nitrogen tetroxide. So like these guys here, we present different kinds of, or how the different conditions change that could alternate, or that could shift the the equilibrium reaction. So I hope this part is clear. Please study this part and read it carefully from your textbook. And if you have any question, I'm waiting for your questions, okay, all the time. Next time, inshallah, we're going to continue our lesson. Thank you guys, and goodbye.